Hello friends, today's question. A wooden block with a coin placed on its top floats in water as shown in figure. The distance L and H are shown there. After some time the coin falls into the water, so we have to find out what is going to happen to L and as well as H when the coin falls from the wooden block. So this is a wooden block, we have coin and the length small l is given the part of the wooden block which is immersed in the water, and h is given as the level of the water from the base. So let us find out for the first case what is going to happen to the wooden block when the coin falls from it. So we are going to discuss this into two parts. First will be initial conditions, which means the coin is over the block, and the second will be the final condition when the coin is going to fall off the block. Initial condition where before coin falls. So this is initial condition, and in this case the coin and block will be acting as one system. So therefore we can say that for coin and block system, we assume or we write some of the parameters which will be associated with the wooden block as well as coin. So we say mass of the wooden block, mass of wooden block, let us suppose is given as capital M. Density of the wooden block, density of wooden block is given as rho block. Then we have volume of the block, volume of wooden block is capital V, and the total height of the block is H, capital H rather, total height of wooden block is capital H, and mass of the coin is, let us suppose, taken as small m. Mass of coin is taken as small m. So these are the few parameters which are associated with coin and block system. And in this case, as the coin and block system is floating, so it means the entire system is in balance. So which basically means the buoyant force which will be acting in the upward direction will be balanced by the weight of coin as well as block which will be acting in downward direction. So we can say buoyant force, and here the block is floating, the block is floating, therefore the buoyant force FB, therefore buoyant force FP must balance the total weight of block and coin, block and coin. So we can say our buoyant force Fp will be equal to capital M plus small m multiplied by g. Let us call this equation number 1. And also this buoyant force will be equal to the weight of the water displaced by the coin block system. Okay, and in the block it will be only dependent upon the, you can say, the amount of volume submerged of the block. So you can say buoyant force is equal to the weight of water displaced by the submerged volume of the block. And let us suppose that volume is given as V block, or rather we can say V submerged. V sub is the volume of the submerged in the, for the block in the liquid. Therefore we can write that the buoyant force Fp will be equal to density of the water multiplied by g and multiplied by the volume submerged of the block. Now if A is the area of the cross section of the block, so you can say for A is the area of cross section for the wooden block, and L is given as a submerged length of the block, and L is the submerged height of the wooden block. Therefore volume submerged will be equal to area multiplied by length. So we can write the buoyant force Fb will be equal to density of water multiplied by G multiplied by A into L. This will be our equation number 2. So comparing equation 1 and 2, from equation 1 and 2 we get m plus small m multiplied by g will be equal to density of water multiplied by g area into length. So g cancel out with g, and from here we can get that the length submerged will be equal to m plus small m divided by density of water and multiplied by g. Let us call this equation number 3. Now we come to the you can say final condition when the coin falls. Final condition and which is after coin falls. After coin falls. Coin falls into the water. So now the weight, the new weight of the block is just the weight of the block, because now there is no block coin system, only the system is consisting of only the block. Therefore we can say that new weight of the block is just the weight of the block, the weight of the block. So we can write weight of the block will be equal to now mass multiplied by g, where m is the mass of the block. Therefore the new buoyant force, which is only going to balance now the weight of the block, so we can say new buoyant force must balance only weight of the block. So we can write Fp prime is equal to now mg. Now once again we are going to find out we say previously we assumed that the submerged volume was V sub. Now we are going to assume that the submerged volume is V prime sub and find out what is the V prime sub. We say the new buoyant force must be equal to the weight of the water displaced by the submerged volume. Weight of the water displaced by the submerged volume. So in this case now we assume V prime sub. So therefore new buoyant force Fp prime will be equal to density of the water will be same, multiplied by G and multiplied by V prime sub. Now area of cross section once again will be A. Let me write it. A is area of cross section, and we assume that the length which is submerged or height is submerged now when the coin falls is now L prime. So L prime is new submerged height. Therefore we can write that our V prime sub is equal to A multiplied by L prime. Therefore we can write our Fp prime is equal to density of water multiplied by G multiplied by A L prime. So we know our Fp prime as well as we find out our Fp prime, that is mg. Okay. And let us call this equation as equation number 4 and this equation as equation number 5. So from equation 4 and 5, equation 4 and 5, we get mg is equal to density of water multiplied by g multiplied by a multiplied by L prime. G cancel out with G, so therefore we can write our L prime is equal to capital M divided by density of water multiplied by A. Let us call this equation number 6. So we already know the value of L. L is equation number 3. So now we're comparing equation 3 and 6. From equation 3 and 6. Let me write it here. Our L was equal to M plus small m water multiplied by area, and L prime is our M upon water multiplied by area. Here I made a mistake, that here it should be G cancels, L doesn't cancel out. Okay, and this will be our area. Okay, I cancelled L. So therefore we can say excuse me, by comparing it can be clearly understood that the denominator is same, only difference is in the numerator. So if we divide them, we get L upon L prime will be equal to M plus small m divided by capital M. And from here we can easily see that M plus small m is greater than capital M, or we can write M plus small m divided by capital M is greater than 1. Excuse me. So therefore we can say L upon L prime is greater than 1, or from here we can say our L is greater than L prime, or L prime is the new submerged height and L is our, we can say, the original height. Okay, therefore we can say the new submerged height decreases. You can say that submerged height, which was L, decreases. Next, we are going to find out about the, you can say, how the small h is going to vary. Okay, so at least from here it is clear that L decreases, so only two options can be correct. L doesn't increase, so this option cannot be correct, as well as this option cannot be correct. Only possibility is that either A is correct or D is correct. Okay, now we are going to find out how our h is going to vary. So we can say that before coin falls, okay, now this is for variation in the height of the water. Height of the water, which is given as h. So once again we are going to say it before coin falls and after coin falls and try to sort it out. So let us consider before coin falls. So in this case, the volume of the water displaced by the floating block will be dependent upon both the mass as well as mass of the block as well as the mass of the coin. You can say that volume of water displaced by the floating wooden block will be equal to, let us suppose that is given as V displaced initial, and this V displaced initial will be equal to weight, that is W. Let me write it here. We get V displaced initial will be equal to weight divided by density of water multiplied by G, and weight will be equal to m plus small m multiplied by G, and this becomes equal to density of water multiplied by G. So G and G cancel out, and this comes equal to m plus small m divided by density of water. Now, after the coin falls, the coin is going to displace the water, which will be equal to its own volume. Coin will displace water equal to its own volume. Therefore, we can say that volume of water displaced by the coin, therefore volume displaced by the coin after it falls will be equal to, let's suppose that is given as V coin, and V coin will be equal to mass oblique density of the coin. One second. Yeah. Now, if you compare the density of the coin as compared to a density of water, so obviously coin is much more denser as compared to water. So we can say that density of coin is greater than density of the water. So therefore, the displaced volume V coin will be less than the mass of the coin. Now, based on this analysis, let us try to find out what will be the net effect on the water level rather, that is given as H. Net effect on the water level, which is given as small h. So now the water level will be determined by the total volume of the water displaced. So you can say that the water level is determined by the total volume of displaced water. Displaced water. And after the coin falls, the total displaced water will be equal to sum of two parts. You can see from here that after coin falls, the total displaced volume, will be sum of, first it will be the volume displaced by the coin. Obviously that volume will be a little bit small, and second one will be the volume displaced by the wooden block. Will be sum of first part, small volume displaced by the coin, small volume displaced by the coin, and second will be volume displaced by the wooden block. Volume displaced by the wooden block. And we have already discussed that the volume displaced by the wooden block, which is reduced because the block rises, which is reduced because block is higher now, because the block is higher now, because as the coin falls, the block rises, so the length or the volume submerged in the water decreases, which we proved in the first part that L prime, the length decreases. Okay. So therefore the new displaced volume, let us call this as V displaced final, and like I said that this will be summation of two parts. This will be two parts giving us a new displaced volume. We can say V displaced final will be equal to, because of the wooden block, plus because of the coin. And we already said that the density of the coin is much larger as compared to water. Density of coin is much larger than the density of water. So from here we can say that mass oblique coin will be much smaller as compared to mass oblique water. Okay. So it means the overall volume, overall displaced volume decreases slightly. So therefore we can say that overall displaced volume decreases slightly. Leading to small drop in the water level. Leading to small drop in the water level. So therefore we can find out that the change in water level let me write it again. We find out change in water level. We can say our delta of V will be equal to m plus m density of water minus m density of water plus small m density of coin. So therefore we can write it that change in volume will be equal to density of water minus m density of coin. And once again, like we proved in the first part as previously, that we said that a density of coin is much larger than density of water. Therefore we can say that m upon density of coin is very small. If m upon coin is very small, so we can just ignore this part, or we can say that the change in volume will be approximately equal to m upon density of water. So which basically means that displaced volume decreases by a small amount. The displaced volume decreases by a small amount. So therefore it leads to slightly decrease in the value of H. So you can say causing water level which is represented as H to decrease slightly, So therefore you can say that both L and H decreases. Let me write it here. So which we can say that L decreases and H also decreases. So the option available to us, so two options we already discarded, that L is not going to increase, so B and C is not possible. So decrease in L was only in A and D. In A, H increases, whereas in D, H decreases. So the correct option will be option number D, both L and H decreases. Option D is correct. So this completes the question. Thank you.